This starts off our notes for section 2 or topic 2, minerals and rocks in the geosphere. And today we're going to start on lesson 1, which is Earth's interior, and it begins on page 48 in your book. So we're learning about Earth's interior. How do we study Earth's interior when we aren't even able to see it? So first and foremost, we're going to discuss evidence, which is the available body of facts or information indicating whether a belief or proposition is true or valid. Scientists focus their methods on two main types of evidence. One is going to be direct evidence, which they get from rock samples, and two is going to be indirect evidence, which they get from seismic waves. Now we're going to work on the Connect It on page 48. On page 49, under figure 1, we have a picture of a rock, and it is titled Rock Hitchhikers. I'm going to read that for you, and then we're going to do Connect It. So, these yellowish-green pieces of rock are xenoliths, from ancient Greek word xeno, meaning foreign, and lith, meaning rock. These xenoliths are fragments of peridotite, a rock that forms at least 50 to 60 kilometers deep inside Earth. They were picked up and carried to the surface by melted rock that later hardened and formed the grayish surrounding rock. So, with that, we're going to go to our Connect It box, and we're going to answer the question under Determine Differences. How did the xenoliths compare to the surrounding rock? So, the gray part was the rock that was all around it, but the xenolith has the yellowish and green pieces, which we know is the peridotite from below Earth's surface. So, under Apply Scientific Reasoning, how might xenoliths help geologists understand Earth's interior? So if we think about that, we know that they were picked up and carried to the surface by melted rock, which means that they were under the surface at some point, and therefore that's going to give us an example of what kinds of things are within Earth's interior. Evidence from rock samples. Drilling brings up many samples of rock and gives geologists many clues. They learn about Earth's structures and conditions deep inside Earth where the rocks are formed. Now we're going to do a wrapped up mystery. What do you do when you have to guess what's inside a package that you can't open? Without changing the package, what kinds of observations can you make that might give you clues about its contents? So, some of the things that we could look at is the size, the shape, its weight, if it's heavy, if it's light. We could look at its color. We can look at its texture. And all of these things are going to tell us a little bit about the package. So our next question, apart from completely opening the package, what could you do in order to give you more information? So you could do things like cutting off a piece, seeing if that shows you what's inside. You can do things like picking it up and shaking it. You can hit it, see how it feels, if it's hollow, if it's not. There's all kinds of things that we can try and we can do to figure out what's inside of things. And a lot of things that you might do at Christmas time when you find gifts under the tree. Evidence from seismic waves. What is a seismic wave? So a seismic wave is a wave that's produced by earthquakes. And it's what geologists use and record to study how the earthquakes travel through Earth. The paths of the seismic waves reveal where the makeup or form of the rocks change, which is ultimately what causes the earthquakes. Let's talk about Earth's layers now. So Earth has three main layers: the crust, the mantle, and the core. The layers vary greatly in thickness, composition, temperature, and pressure. The pressure gets increased the deeper you go. So the further down you go, or the closer to the inner core you go, the greater the pressure is going to be. The temperature inside Earth also increases as depth increases. So the further down you go, the closer to the inner core you get, the hotter it's going to be. All right, pressure and depth, figure 3. So on page 51 in our textbook, we have the pressure and depth activity. So the deeper that the swimmer goes, the greater the pressure on the swimmer from the surrounding water. Number 1, compare and contrast. How is the water in the swimming pool similar to Earth's interior? How is it different? We're going to do the hint to consider that both temperature and pressure should be in your answers. So, as we're swimming and we go down further and further, we're going to feel more pressure the further down we go. However, typically in a pool, the further down you go, the colder the water is going to be. Now, if we're in a temperature-controlled pool, we're not going to notice it because, well, the temperature is controlled in the pool. But if we are just outside in a pool that's outside, for example, if we're at the community pool here in town, that pool, the further you go down, the cooler it's going to be because it's warmed by the sun, and the sun's only going to warm the top layers of the water. It's not going to be able to permeate all the way down. So, in that instance, the further down they go, the greater the pressure is, which is similar to moving down Earth's core. However, the temperature is going to be different because the temperature decreases as you go down. But in regards to the core, the temperature increases the further you go down. So question 2, at what location in the pool would the water pressure be the greatest? So if the pressure increases the further we go down, then it's going to be at its greatest pressure at the bottom of the pool, right? Because if the pressure increases, the further you go down, and the lowest point you can go is the bottom of the pool, that's where the pressure is going to be the greatest. So the first layer in Earth's system is the crust. The Earth's crust is the rock that forms Earth's outer layer, a layer of solid rock that includes both dry land and the ocean floor. Elements consist of only one kind of atom and cannot be broken down. The main elements in the rocks in Earth's crust are oxygen and silicon. The crust is the thinnest of the three layers, usually between 5 and 40 kilometers. There are two types of crust. There's the oceanic crust, which lies beneath the ocean, composition like basalt, a dark fine-grained rock. And then there's continental crust, which forms the continents, compositions like granite, a light-colored, coarse-grained rock. The next layer of Earth is the mantle. Earth's mantle is a layer of hot rock that contains more magnesium and iron than the rock above it. Overall, the mantle is nearly 3,000 kilometers thick. The uppermost part of the mantle is brittle rock, like the crust. The lithosphere, which a name is given to the crust and uppermost mantle together, is about 100 kilometers thick. The asthenosphere, which name is given to the hotter, solid, bendable layer below the lithosphere, and then the lower mantle, which is beneath the asthenosphere, which is the hot, rigid, and under intense pressure. So, in the image here to the right, we have the crust, and then we have the uppermost part of the mantle, And that together shows the lithosphere. Then underneath that, we have the asthenosphere, and then we finally have the lower mantle. On page 53 in your textbook, I want you to use this information, which is also shown in the textbook on that page, and complete the line graph. So you're going to plot each point. So you're going to go to 500, which is going to be your first line on the bottom, and then you're going to go up to the temperature 1600, which is going to be just past the mark halfway between 1000 and 2000 in temperature. You're going to mark there. Then you're going to go to 1000, which is the next one, and you're going to mark 18, which is going to be halfway between the 1500 mark and the 2000. And you're going to continue until you have all of your dots placed, and then you're going to draw a line that follows those. Then I want you to answer the question, how does temperature change with the depth in Earth's mantle? And if you drew your map correctly, the temperature is going to increase rapidly with depth in the lithosphere, more slowly in the asthenosphere, and most of the mesosphere, and then it's going to heat even more rapidly in the lower mantle and above the core. The final layer is Earth's core. And so the Earth's core is the dense part of the planet, and it consists of two parts. The outer core, which is a liquid layer made of molten metal surrounding the inner core, which is about 2,260 kilometers thick. And the inner core is a dense ball of solid metal, and it's about 1,220 kilometers thick. Both parts are mostly made of iron and nickel, with small amounts of oxygen, sulfur, and silicon. Based on the information that we covered in the last slide in your textbook, we are going to fill out the information on the modelet on page 54, which is represented here. So, to begin with, what was the thickness of the crust? So right here, we're looking for 5 to 80 kilometers. The composition of the crust here is made up of something like granite or basalt, and it is a solid. Then you have the mantle, which is 2,800 to 2,890 kilometers, right here. Its composition is made up of magnesium and iron, and it is also a solid. The outer core is 2,260 kilometers in thickness. It's made up of iron and nickel, and it is a liquid. The inner core is made up of 1,220 kilometers, and its composition is also made up of iron and nickel. And like the majority of the other cores, the inner core is also a solid. So the total thickness of Earth is going to be 6,370 kilometers. So we're going to pick any 2 points inside Earth and label them A and B. So if we were to put one as in your picture on page 55, if we put one in the dark orange, we would then label that the mantle. And then if we put the other one in the white section, we would label that the inner core. Now we're going to compare and contrast Earth at these 2 points. So Earth at point A is colder than Earth at point B. The pressure is greater at point B than at point A, and Earth at both point A and point B is solid. The core and Earth's magnetic field. Scientists think that the movements in the liquid outer core produce Earth's magnetic field. Iron fillings around a bar magnet will line up in a pattern matching the magnetic field. Similarly, if you could surround Earth with iron fillings, they would form a similar pattern, like a compass. The compass needle aligns with Earth's magnetic field. Reading check. How can iron fillings provide evidence that a bar magnet has a magnetic field? When the magnet is lying flat and iron fillings are sprinkled around the magnet, the fillings line up in a specific pattern. And that would be our answer. Movement in Earth's mantle. Heat is a form of energy that flows. Heat flows from matter at a higher temperature to a lower temperature, which is convection currents. So the reading check that goes along here is cause and effect. What three processes or forces combine to set convection currents in motion? 1. Heating and cooling a fluid. 2. Changes in a fluid's density. And 3. The force of gravity. Convection currents in Earth. Heat from the core and mantle drive convection currents. Oceanic lithosphere cools and sinks and drives the mantle's convection. Cold lithosphere moves down into the mantle where it's heated. An upward flow of hot rock completes the cycle. One full cycle takes millions of years. Convection currents are involved in the production of new rock at Earth's surface, and it occurs at the outer crust as well. Now that we've finished our notes for this lesson, we're going to go ahead and do the lesson check. So number 1, name each layer of Earth, starting from Earth's center. So we have the core, the inner and outer, and we have the mantle, and finally the crust. 2, give examples of direct evidence and indirect evidence that geologists use to learn about Earth's interior. Direct evidence would be rocks from deep inside Earth that volcanoes bring to the surface when they erupt. Indirect evidence are passive recorded seismic waves that indicate changes in the makeup of rocks inside of Earth. 3, what would happen to the convection currents in the mantle if Earth's interior cooled down, and why? The currents would stop because a difference in density, caused by heat, is needed to drive the currents. How does convection cause movement of material and energy in Earth's interior? So, cool, dense rock from the lithosphere sinks into the mantle where it is heated again. The heated, less dense rock flows upward. This moves both heat and material. 5. How is the rock in the deep mantle similar to the rock in the parts of the mantle nearest the surface? How are they different? Rock in all parts of the mantle is moving due to convection currents. The rock nearest the surface is colder, denser, and sinking. Rock in the deep mantle is warmer, less dense, and rising. Now, I would like to do the quest check-in. So, that is under it, and it says, in this lesson you learned about Earth's interior and also how energy and material move between Earth's interior and its surface. So we're going to explain why you think it is or isn't important for science fiction films to depict natural processes and geological events as accurately as possible. I would like you to answer this so that we can discuss it further in class tomorrow.